Hi everyone. Today we are discussing about Fourier series and LTI systems. Fourier series and LTI systems. Consider a LTI system, linear time invariant system, with input x and output y, and the frequency response h of j omega is represents x of t equal to summation of k equal to minus infinity to infinity ek e power jk omega naught t, where omega naught is equal to 2 pi by t. That means these are the related formulas of LTI systems. These are the related formulas of LTI systems. Next we are entering to the other topic, filtering. Filtering. In many applications, we want to modify the spectrum of a signal by either amplifying or attenuating certain frequency components. Filtering means mixing. In many applications, we want to modify the spectrum of a signal, either amplifying or attenuating certain frequency components of certain frequency components. In this process, modifying the frequency spectrum of a signal is known as modifying frequency of a spectrum signal is known as filtering. Filtering means modifying, either amplifying or attenuating. That means we can change the values from high state to low state or low state to high state, top to bottom, bottom to just we are changing, interchanging, exchanging, or modifying. Everything will be known as filtering. A system that performs a filtering operation is called a system that performs a filtering operation is called filter is called filter. Many types of filters exist. Frequency selective filters pass some frequencies with a little or more distortion, while significant attenuation are other frequencies. Several basic types of frequency selective filtering, including low pass, high pass, and band pass filters. Low pass, high pass, band pass filters. Why we are using low pass, high pass, band pass filters? Why we are using low pass, high pass, and band pass filters? By using low pass, high pass, band pass filters, those who are helpful, those are more helpful to adjusting the frequency levels from different states, either high to low or low to high. By using band pass and low pass and high pass filters, it will providing additional frequency of the signals that is more helpful to transfer the information from one place to another place. That is more helpful to transfer the information from one place to another place. That's why we are using different frequency bands or filters. They are called low pass, high pass, band pass. Filter means mixing. Next one is ideal low pass filter. Already in previous slide we know why we are using low pass, high pass, band pass filters. Low pass, high pass, band pass filters. By using low pass, high pass, band pass filters, by using low pass, high pass, band pass filters, we can adjusting the frequency levels from any stages. In an ideal low pass filter, eliminates all frequency components with a frequency those magnitude is greater than sum of some cutoff frequency while leave the remaining frequency components unaffected. An ideal low pass filter eliminates all frequency components with a frequency whose magnitude is greater than some cutoff frequency, the learning frequency components unaffected. Such a filter has a frequency response of the form. Here, frequency response of the form h of j omega is equal to 1 for mod omega is less than or equal to omega c, 0 otherwise, where omega c is the cutoff frequency. A plot of this frequency response is given by a plot of this response is given by waveform representation from various bands like stop band and pass band. What is stop band and what is pass band? What is stop band and what is pass band? Stop band is nothing but there is no wave will be propagates on that particular period. There is no wave propagation is not propagates on that particular time period. Pass band means active band. Pass band means active band. That means it will share the information on that particular period. It will share the information on that particular period. So that's why we are no pass band and stop band. Stop band means they are not use any frequency at that period. They are not propagate any signal at that period. Pass band means it will propagate the data information easier and faster to the next stage. So that's why we are using different frequency bands, and these are the different differences between pass band and stop band. Next one is ideal high pass filter. An ideal high pass filter eliminates all frequency components with a frequency whose magnitude is less than some cutoff frequency, while leaving the remaining frequency components unaffected. That that is the meaning is represent. That meaning is represents both active and stop band and pass band representations. The ideal high pass filter eliminates all frequency components with a frequency whose magnitude is less than some cutoff frequency. That means 0. That means less than some cutoff frequency at that period. The signal is does not propagate from output side. The signal is does not propagate from output side. The signal is does not propagate from output side. Such a filter has frequency response form, and the frequency response is represents h of j omega is equal to 1 for mod W greater than or equal to omega c 0 otherwise, and this is the another form of various bands like pass band and stop band. Here just we are changing the polarities, mod omega greater than equal to omega c cutoff frequency. Here also the wave is propagates from left and right sides. The wave is propagates from left and right sides. That means in the middle of region there is no signal will propagates from one place to another place. That's why it is represents as a pass band and a stop band. Here omega c is the cutoff wavelength and h is the function of the frequency. Next one is ideal band pass filter. Ideal band pass filter. In previous we are discussing ideal high pass filter, ideal low pass filter, ideal low pass filter, ideal high pass filter, ideal band pass filter. And what is the differences between both ideal and high band low band pass band filters? In this also we are observing the plot of frequency response is splitted compared to the previous waveforms. It will divided multiple equal parts. Why? Because we are changing the formula condition. Cutoff wavelength 1 less than or equal to mod cutoff frequency less than or equal to cutoff wavelength 2. 0 otherwise means that is a stop band region. Here 1 represents data propagation, 1 represents data propagation, and 0 represents data not propagation. In data propagation, pass band will be activated, otherwise stop band will be propagated. The overall concept of in this filters, when we are propagate signals from one place to another place, at that time, at that time, the pass band will be activated, otherwise stop band will be activated. Once again, I will repeat why we are using these type of filters, either a band pass filter or high band pass filter, low pass filter, high pass filter. Why we are using these are all? These are all using to conversion of signals from various techniques with the help of frequency response time and amplitude. Next one is continuous time Fourier transform. In previous we are discussing FT Fourier transforms. Now we are entering to the new topic, that is continuous time Fourier transform. Motivation for Fourier transform. Motivation for the Fourier transform. Fourier series provide an extremely useful representation for periodic signals. Periodic signals. Fourier series provides an extremely useful representation for periodic signals. After, however, we have to need to ideal these signals. that are not periodic. That are not periodic. A more general tool than the Fourier series is needed in this case. A Fourier transform can be used to present both periodic and aperiodic signals. Since the Fourier transform essentially divides Fourier series through the through a limited process, a Fourier transform has many similarities with Fourier series. That means the overall concept of Fourier series or Fourier transforms all are it will be used to represents the behavior of the signals and it will represent some several conditions how to change the signals from one place to another place or transfer the information with various regions with various regions either pass band or stop band. Next one is Fourier transform. Development of Fourier transform. Development of Fourier transform. The Fourier series an extremely useful signal representations. Upper state, lower state conjugation signals and pass band, low pass, high pass, band pass. So that means the behavior of the signal will be represented by using Fourier series is an extremely useful signal representation. Fourier series. Unfortunately, this signal representation can only be used for periodic signals. Since Fourier series is an inherently periodic, many signals are not periodic. However, rather than abandoning Fourier series, one might wonder if we can somehow use Fourier series to develop a representation that can apply to periodic signals. By viewing and periodic signals that has limited case of periodic signals with period t tends to infinity, we can use the Fourier series to develop a more general signal representation that can be used both periodic and periodic signals. The signals most representation is called Fourier transform. So the overall concept of Fourier series it will represents like several representation signals are transferring several signals from one place to another place to share or transfer the information easier and faster and represents various conversions left to right, right to left, or top to bottom, or bottom to top. Already in previous classes, we are clearly observe the behavior of the signals when we are changing the amplitude, time, and phase of the signals with respect to the Fourier series or Fourier transforms. By using Fourier series and Fourier transforms, it is like a system which converts the signals in different forms. Next, we are entering to the main topic continuous time Fourier transform CTFT. Continuous time Fourier transform. A continuous time Fourier transform of signal x denotes f of x or x is given x of omega is equal to integration of infinity to infinity మీకేమైనా అవసరం అయితే ఉంచుకో ఉన్నాయా? The continuous Fourier transform, the signal x is denotes x, f of x or x is given by x of omega integration of x of t e power j omega t dt. The processing equation is sometimes referred to as a Fourier transform analysis equation or forward Fourier series equation. The inverse Fourier series transform of x denoted f inverse of x, x is given by x of t equal to 1 by 2 pi integration of infinity to infinity x of omega e power j omega t dt. The preceding equation is sometimes referred to as a Fourier transform synthesis equation or inverse Fourier series transform equation. As a matter of notation, to denote that the x of the has the Fourier transform x, we write x of t equal to x of omega. Small x of t equal to x of omega. Small x is the inverse Fourier transform. Capital X is the Fourier transform, and small x of t is the inverse Fourier transform. And these are the differences between Fourier transform and inverse Fourier transform. Now we are entering to the other topic, convergence properties of the Fourier transform. Convergence properties of the Fourier transform. Convergence properties of the Fourier transform. In this convergence of the Fourier transform, consider an arbitrary signal x. The signal x has the Fourier transform representation x bar is given by x bar of t equal to 1 by 2 pi minus integration of minus infinity to infinity x of omega e power j omega t dt, and where x of omega is equal to minus integration of minus infinity to infinity x of t e power j omega t dt. How need to how need to concern ourselves with convergence properties of this representation. Here we are seeing different formulas, both all are more useful for data convergence from Fourier transform or continuous Fourier transform. These are also convergence of the Fourier transform continuous case and different condition equations. It is helpful for to simplifying the problematic equations. For example, what is the formula for x of t in convergence of Fourier transform? X of t equal to 1 by 2 pi integration of minus infinity to infinity of integration of minus infinity to infinity x of t power j omega t dt. Next, convergence of the Fourier transform energy case. Finite energy case. In a signal axis of finite energy, in a signal axis of finite energy, for example, integration minus infinity to infinity mod x of t whole square dt less than infinity, then its Fourier transform representation coverage is the MSE sense mean square error. So by using these are all formulas, we can calculate number of problematic equations easier and faster. And I think it is enough for no different formulas and different equations. And next class we know other topics and other importance of other meanings and why we are using this type of Fourier series in other applications. All are you all are we are seeing to the next class. Thank you.